So the topic of this talk is, like I said, distributed approaches to mirror descent. We're really interested in stochastic learning in the form of stochastic optimization over networks with rate limitations. And to illustrate the idea, I'll give you an example that's relevant to my hometown. So I live in Detroit, and so I'm going to start off with an example that is relevant to the automotive industry, which gets talked about a lot on my campus. So consider autonomous driving. So we have some network of autonomous vehicles, and you might know that the bigger challenge with autonomous driving is not so much getting cars to drive on the road very well. It's getting them to drive on the road very well while interacting with humans, and in particular human operated vehicles. And so one thing that we're definitely going to have to do before autonomous cars are on the road is pack them full of sensors that look around for anomalous driving on the part of a human-driven car. And by anomalous driving, I mean bad driving, like it weaves out of its lane or it suddenly brakes or something like that. And what these autonomous vehicles want to do is sense an anomalous event and then predict where the car is going to go so that they can avoid an accident. And they want to do this in a cooperative manner, sensing, using all of their sensor measurements, and then collaboratively over their communication links, jointly and coordinatedly avoiding an incident. This presents some challenges. First of all, they need to act very, very quickly. They don't really have a lot of time to dally around. The other problem is that these wireless links have rather limited rates. You know, they may be fast, but they're not going to be that fast. They're certainly not going to be fast enough that these nodes can exchange raw data. And so they're going to have to do something else. And so at a high level, the talk is about solving problems that look like this. Over these kinds of sensor and decision networks, how well can devices jointly learn when the links that connect them are slow or at least not particularly fast? And then what are good strategies for doing so? And in this talk, we're going to frame this as a distributed stochastic optimization problem. So that's to say we're going to have a network of devices that are trying to minimize some objective function from streams of noisy data. And we're going to focus on the communications aspect. So how are we going to collaborate when the links have limited rates? And so part of the contribution is just framing this problem in the right way. And the way we're going to do this is by defining two timescales. There's going to be a timescale on which data arrive at the individual devices. And then there's going to be a rate at which they're allowed to exchange messages for coordination. And we're particularly interested in the case where this rate of message exchange is small relative to the rate of data arrival. And then we're going to look at how well can one do learning, stochastic approximation learning in this environment. And so our solution is going to be distributed versions of stochastic mirror descent. And so contrary to the previous talk, we're going to focus on first-order methods. And the distributed component of this is going to balance a gradient averaging by means of averaging consensus, and then mini-batching, local mini-batching, so that we can effectively slow down the rate at which the data arrives relative to the rate at which nodes can exchange messages. And we're going to drive conditions under which these approaches give us near optimum convergence speed. That is, with respect to any other stochastic first-order method. We're going to find something that's kind of fun. In this case, in the decentralized case, using accelerated methods are going to provide a substantial speed up in a way that they don't so much in centralized settings. OK, so let's be a little bit more formal. So our network looks like the following. We're going to have a network of M nodes, each of which has some IID data streams. So we have C of I is the sensor, T is the time index, and then each node has some data stream. And these nodes are going to communicate over wireless links that are going to be modeled by some graph. We'll detail this we'll put this in more detail in a few more slides. And what these nodes want to do each is solve a stochastic optimization problem. So again, by contrast to the previous talk, we're going to focus exclusively on the minimization of a stochastic problem where we are minimizing some function that is the expected value of some different function that's a function both of our search variables, x, and the data variable, c, and where, of course, we suppose that the distribution over c is unknown to the devices. We are going to suppose that our objective function is convex, and we're going to suppose that we're optimizing over a compact and convex subset of RD. And we're going to make a few more standard assumptions. First of all, we're going to suppose that our objective function has Lipschitz continuous gradients. That's to say it's smooth, or at least smooth enough for convex optimization. Later, if there's time, which I kind of suppose there won't be, we'll talk about what happens if we suppose composite optimization. What happens if we incorporate non-smoothness into this scenario. Okay, we're going to suppose that nodes have access to noisy gradients. In the parlance of the literature, we say they have some oracle that at every time a data sample arrives, the nodes can query this oracle and get some noisy version of the gradient. So GIT, we define this as the gradient evaluated at a search point, xi, that each node carries for each time step t, and then its data point. And it's easy to convince yourself, of course, that the expected value of this gradient is equal to the true gradient. And we suppose further that the gradient noise has bounded variance. So there's some sigma squared that bounds the variance. And like I said, each node is going to keep its own search points, xit, as it searches for something close to the minimizer of this problem. Now, one possibility is that you could just let each of these nodes go it alone. They have this incoming stream of data, and you could just think of this as a centralized stochastic optimization problem. And this is well understood. Again, if we restrict ourselves to this gradient oracle method, so we restrict ourselves to first-order methods, we can get optimum convergence via stochastic versions of mirror descent algorithm. So very simple special case of the stochastic mirror descent problem is that we initialize the iterations at some point, and then we just do continuous projected gradient descent rounds. We take a gradient to step, and then we project it onto our convex constraint set. And then as we go, we keep track of the average of the iterates over time. And it's proven, and if you're familiar with mirror descent, you know that this is the vanilla stochastic mirror descent, that you can extend this via Bregman divergences and more complicated prox mappings to speed up the convergence in some cases. In any case, after t rounds, it's proven that this stochastic mirror descent has convergence that looks like the following. The gap, the expected gap between the iterate at each node and the true solution is on the order of L over T, where L was the Lipschitz constant in our gradients, and plus sigma over T, where again sigma squared is the noise variance. Now this first term is not something that you can improve upon for first order methods. This 1 over square root of T is the best you're going to do. But in Land, this second paper here, a more complicated version of mirror descent that I'm not going to detail. Basically, it uses the same sort of projected stochastic gradient descent steps, but uses more complicated iterate averaging that puts preference towards the later iterates in the sequence. Gives us a slightly better bound on the error. So in particular, after t rounds of this accelerated stochastic mirror descent, the error is on the order of L over T squared plus sigma over square root of T. Now, if sigma is substantial, if we have substantial gradient noise, this is the term that dominates. And it doesn't matter too much that we got this acceleration over here, at least in terms of order-wise convergence. But the nice thing about this, we usually talk about this in terms of universality. We have a single algorithm that, if you have noise, gives you this sigma over root T convergence. And if you turn out not to have noise, then it gives you the L over T squared convergence that happens in the deterministic case. And the nice thing about this is that this is the best you can do, regardless of the noise situation. What we're going to find when we distribute this algorithm is that it's going to turn out to matter. This difference between T and T squared in this first term that corresponds to deterministic first order methods is going to turn out to matter in the distributed case. Okay, so back to the distributed case. So we have M nodes, and after T rounds of data collection, there have been MT gradients that we could use. And so the ideal case, the best possible performance is that we have something that looks like sigma over square root of MT instead of T, and then with a similar speed up in the deterministic term. And indeed, this would be possible if your communications were sufficiently fast. It'd be straightforward to just share all of your data, get all your gradients around, and get performance like this. There's been some previous work in some different environments that try to get at this as well. So a paper that is probably of most immediate interest is a paper by Deckel et al. in 2012, where they're looking at this in more of a parallel computing, a distributed computing environment, where they spread the data out, and then using all reduce, basically building a spanning tree over the nodes, they compute the averages of the gradients. And by taking the average of the gradients, then taking a stochastic mirror descent step, they manage to get this sigma over square root of mt term. And the reason this works is because they reduce the gradient noise, and that gives you the speed up exactly proportional to the number of nodes that you have. Now, this makes a lot of sense in the distributed computing environment. We've got this kind of structure. In wireless networks, this is a little bit harder. And so there's also a lot of work. In fact, there's too much work to detail it all here. So there's a few representative papers where gradient averaging is taken care of by means of average consensus, somewhat similar to what we're doing in this paper, but different. Or incremental methods where the solution sort of passed from node to node throughout the network. These are ways that people have tried to deal with this problem in more wireless setups. Okay, so that's the optimization model. Now, the communications model, we said earlier that we're going to have nodes that are connected over some undirected graph, and this graph is represented by a set of vertices, one corresponding to each device, and a set of edges, one corresponding to each pair of devices that are connected by some wireless link. And we suppose that every communications round, each node is allowed to broadcast some message out to all of its neighbors, and also receives a message from all of its neighbors. And we suppose that the rates are limited, and we model this rate limitation by what we call a communications ratio, which is some positive number that tells us how often communications happens relative to how often data samples arrive. So we say that we have row communications rounds for every data sample that arrives at each node. And so you can think about it like this, that if I have data samples, if I have data samples that are indexed by time t, if rho is equal to 1/2, then I'm only going to get a communications round for every 2 data samples. Similarly, if rho is equal to 2, then I'm going to get 2 communications rounds for every data round, and therefore I'm going to get multiple rounds per data point. Big rho corresponds to fast communications rate. Small rho corresponds to smaller communications rates. Now, this communications model leaves a lot of stuff out. We assume a graph, and so we're sort of implicitly ignoring interference. We're not really worrying about delays. We're just worried about rate. How often can I talk to the people around me? Okay, so the basic idea of the methods that we're going to propose are to distribute stochastic mirror descent via averaging consensus. So each node is first of all going to obtain its own local gradient from its own local data set. And then via averaging consensus, which I assume most of you are familiar with, in a slide or two we'll discuss in a little bit more detail, they're going to compute approximate averages of the gradients and get good reduction in the noise variance. And then with these less noisy gradients, they're going to take a mirror descent step. And so to be really clear, what's going to happen is that each node is going to update its search points once per data round, at most. And so again, if rho equals to 2, then I get 2 consensus rounds per data step up, and then per search point updates. Now the truth is, this is not very good. Using only 2 rounds for a consensus isn't going to allow you to compute very close averages. And so if rho is small, if our links aren't fast enough, then we are not going to be able to really process the data samples, get the good averages that we want, so we can get the gradient points we want before the new data samples arrive. The network will be overwhelmed by the data that it's meant to process. So we're going to solve this problem via mini-batching. Now, mini-batching is not new. It's used ubiquitously in both centralized and distributed optimization problems. But let's go through it just a little bit in detail. So first of all, we're going to pick a batch size, b greater than or equal to 1. It's got to be an integer, of course. And the choice of the batch size is actually going to matter a lot in this case. And each node is going to hold its search point constant for b rounds. And then over that b rounds, it's going to keep collecting gradients evaluated at the same point, and then average them together. And so for each search point, or each mini batch round that we index by s, there's going to be a collection of b gradients, each of which now is going to have gradient noise equal to sigma squared over b by just the very nature of computing these averages. What this allows us for is more consensus rounds. So if I have a rate equal to 1/2 and I don't even get a single consensus round per data point, and I use a mini batch size of 4, well, now suddenly I get 2 consensus rounds in not for every data sample, but through every mini batch gradient. So what's going to happen is I induce a trade-off where I get more consensus rounds, and each of the gradients that I'm computing with respect to the mini batches is going to have smaller gradients. However, I get fewer search points updates. And balancing this trade-off is going to turn out to determine whether or not we get order optimum convergence or not. OK, so just a reminder of how gradient averaging works. So averaging consensus, the idea behind it is that nodes exchange messages with nearby neighbors, compute local averages of the gradients by their nearby neighbors. And then over time, if we do it right, this converges on the global average with high probability. So what we do is we choose a doubly stochastic matrix W, that's M by M, such that its entries are only non-zero if the nodes are connected. And then at mini batch round S and every communications round R, each node computes a sum. They say take the averages from the previous communications round and just average those of my neighbor together by the constants determined by this matrix. So if we have a mini batch size B and a communications ratio R, then nodes can carry out B times rho consensus rounds per mini batch. And then, of course, as B times rho goes off to infinity, it's easy to show that this process converges on the true average of the gradients. Now, averaging consensus has been used, again, rather a lot in distributed optimization. Here are a few recent-ish papers that involve it. Again, the amount of prior literature is too much to cover in detail here. So again, this is the equation for the consensus estimates. And so we get a lemma, which is that the equivalent gradient noise is bounded by the following. So we call this sigma squared EQ, the equivalent gradient noise. And that's just the gap between the mini batch average and the true gradient that you're after. It has 3 terms. I'll actually go in reverse order. Sigma squared over MB is the ideal case. If you would manage to compute a perfect average, this is the variance that you would have. And then you have 2 terms that are left over due to imperfect consensus averaging. So in the first case, I don't compute a perfect average, so there's going to be some residual left over. And it has sigma squared over B times sigma, this lambda 2, which is the second largest eigenvalue of the matrix W. And then similarly, we have a term that corresponds to gaps in node search points. So if we don't compute perfect averages, nodes are going to take gradient steps. They're going to slightly diverge over time. And that divergence in particular could compound over time if we don't use enough consensus rounds. And so again, for P or B large, these terms go away, and we end up with the perfect average case. OK, so putting all the pieces together, we get the first algorithm that we call distributed stochastic approximation mirror descent. We call it DSAMmed. I won't go through all the steps. Basically, what happens is we have an outer loop where each node computes its mini batch gradients, and an inner loop where each node takes rho B consensus steps in order to come up with better versions of the averages of the gradients. And then after the mini batching, you go ahead and take the standard mirror descent step, and you move on. Now recall that mirror descent has the following convergence rate, L over T plus sigma over square root of T. Well, if we put in the equivalent noise variance, and we consider the fact that our mini batching is going to reduce the number of search point updates we do, or the number of mini batch, or the number of mirror descent steps we do, we end up with the following. The convergence rate now is a little bit different, where we get a B over T over here because we take fewer steps. Same thing over here, except now we have sigma squared EQ. It's just the equivalent noise variance. And so the question is, how do we choose B? We need to choose it big enough to make sure that this term doesn't blow up. And furthermore, what we'd like to do is choose it such that this equivalent noise variance is on par with the residual noise variance. We'd really like to have this term dominate. And so if you sit down with that equation and you work out how hard you need to work, you get that you need mini batches that are on the order of this size, where you have a 1 because you can't have mini batch size less than 1. And it scales as log mt over rho times log of 1 over the second largest eigenvalue of the mixing matrix. So what happens is the larger the network gets, or the slower the communications, the larger B needs to be so that you can take more and more gradient steps in order to get good averages. And so this guarantees that that error term doesn't blow up. It's also sufficient to guarantee that the overall equivalent noise is on the order of the optimum noise. And so this gives a convergent rate that looks like this. We have this term over here due to the use of the mini batch size. And then the second term, the noise term, I just lost my pointer. And the noise term is exactly order optimum. So the question is, when is this order optimum? It comes down to when this term becomes the one that dominates. And so again, you can sit down and do some math on the previous result, and you get that as long as rho is bigger than this term here on the right-hand side, then the conditions of the previous lemma guarantee that the expected error in convergence is equal to a term that's on the optimum order. So what that means is, again, the larger the network, the larger the communication rate needs to be in order to have order optimum convergence. Furthermore, this log of 1 over sigma squared w says that the connectivity of the network matters a lot. So if the topology is such that it's very difficult for nodes to compute global averages from local averages, then you're going to need a higher communications rate because you're going to need more consensus rounds in order to get to order optimum gradient noise. And so what happens here is that if the communications rate gets smaller, we'll take larger and larger mini batch sizes to compensate to get the overall equivalent gradient noise down. The noise term doesn't care. As long as I mini batch, I reduce the gradient noise, and the noise term in the convergence rate just doesn't care. But the first term, the 1 over t term, cares about how many steps I take. And the more and more we crank up the mini batch size, the fewer and fewer steps we take, and eventually that deterministic term is going to dominate the convergence rate. And so once we get to that point, we get to that point when the rate does not satisfy this condition. Now, since this deterministic term is the thing that's giving us trouble, a natural idea is to just go ahead and use accelerated mirror descent. It should allow us to do more aggressive mini batching and should give us a better handle on the convergence rates. So sure enough, recall that accelerated mirror descent takes a similar stochastic projected gradient descent, and it just uses more complicated averaging. And we can do basically the same thing, except using accelerated mirror descent updates instead of standard mirror descent updates. And so I won't go through the details again. This is just very, very simplified pseudocode. We're doing the same thing. Perform consensus on the mini batch gradients, and then perform accelerated mirror descent. And the analysis turned out to be rather similar for this accelerated distributed mirror descent case. So now this first term is the equivalent L over B squared T squared, owing to the fact that accelerated mirror descent has a 1 over T squared term as its deterministic term. And it turns out if you sit down and do the analysis that the equivalent gradient noise has approximately the same variance, so that order-wise this is the same term. And so again, you need about the same mini batch size in order to guarantee that the iterates don't diverge, and in order to guarantee that the equivalent noise is optimum, order-wise optimum. And so the only real difference here in the analysis is that because the convergence rate at the deterministic part is more flexible, we end up with a different term out front when we plug in the necessary mini batch size. And we end up with a more generous condition on the communications rate that we need. And so before, the condition on rho was that it was equal to m squared in the numerator, and m to the 1/2 in the numerator and t to the 1/2 in the denominator. In this case, we get that improvement of 1/4 in both of these exponents. And so the network can grow a little bit more slowly, and the total number of consensus rounds doesn't have to grow quite as quickly for this communications rate to be order-wise optimum. How am I doing on time?
9 minutes.
Okay. Well then, so I'll just show you a very quick example. So we just tried this out on very simple logistic regression in 50-dimensional space on a network of 20 nodes, just using the log loss cost function. Nothing fancy in the optimization problem that we solved. We did this for rho equal to 1, so relatively slow communications, and rho equal to 10, faster communications. And then we have on the top, the blue is the distributed non-accelerated mirror descent. Red is the accelerated case. And then the other two curves are centralized case. What if all the data were in one spot and you didn't have to worry about it being distributed in the first place? And so obviously the accelerated case works faster. Obviously the faster your communications rate, the better. But then also when rho is equal to 1, in this case the mini batch size turns out to be a lot bigger. And you see this sort of staircase thing where the nodes are holding their search points constant over time. Because that's the optimum thing for them to do to make sure that their iterates don't diverge. Okay, since I do have a little bit of time left, I'm going to talk about composite optimization before I close up. So what if the objective function is not smooth? We can consider the case of composite convex optimization, where f of x is kind of like before. This is a Lipschitz function who also has Lipschitz continuous gradients. But then this function h is not necessarily differentiable. It is a Lipschitz function itself, but in general it's not differentiable. That's what makes it interesting. So it's shown in LAN that if you do accelerated mirror descent via subgradients instead of using gradients, you get optimum convergence. And the convergence speed is just a little bit different, where instead of just sigma over square root of t, you have m plus sigma over square root of t, where again this m is the Lipschitz constant on the non-smooth part. So the challenge with the non-smooth part, of course, is that small perturbations in the function could perhaps give you large perturbations in the subgradients. And so in a very loose, intuitive sense, the Lipschitz constant associated with the non-smooth function is sort of like the noise variance associated with the subgradients. It's how much it's going to deviate. And this presents a couple of challenges for our algorithm. So first of all, mini-batching doesn't help, because if I mini-batch, I reduce the gradient noise, but the non-smooth part doesn't really care, because as long as I perturb the iterates a little bit, I potentially suffer the entire loss of the non-smooth part. And so I can't use mini-batching in order to make this entire term go faster. I can make the noise go away, I can make the noise smaller, but the non-smooth part doesn't really care. And that result changes this term to be something that is now strictly suboptimum, pretty much no matter what, as long as that constant m is actually held constant. The other problem is that imperfect average consensus results in a noise floor. That's because, again, if I don't perfectly average the gradients, I'm going to have small variations in the iterates at different nodes. And so they're always going to be computing gradients at just a little bit the wrong spot. And so those subgradients are going to differ, again, by a factor as much as m, and that's going to give us this noise floor that no matter what, we're going to be sort of hovering around the optimum. And so one of the potentials for future work is to see how to fix this algorithm in the case of non-smooth objective functions. Okay, with that, I'll sum up. So we looked at stochastic learning from the perspective of rate-limited links, particularly in the wireless perspective. And we developed two schemes that we call DSAMmed and ADSAMmed that take stochastic mirror descent and balance in-network gradient averaging via averaging consensus and local mini-batching to slow down the effective rate of the data. And then we derive conditions for order optimum network convergence, that is to say, conditions on the rate. And so, like I said before, future work involves doing something about the suboptimality in the performance for composite objective functions. Also, we gave conditions where ADSAMs or even DSAM have optimum convergence rates. But are those conditions the end of the story? Probably not. They're probably things we can do to either be via better analysis or better techniques improve the convergence rates. And then also we left out a lot of communications issues that are of interest. What about delay? What about quantization? We sort of suppose that you could send perfect gradients over this network defined by the graph. What happens if you can't do that? So the things that we're interested in. Then we have a preprint available that if you want to see more details and more rigorous proofs that I invite you to check out. Thank you.
We have 2 to 3 minutes for questions.
So your raw parameter, right, the communication speed, that's something here, constant all over the network and also over time.
Mm-hmm.
So, okay, this might not be practically, realistic assumption, but apart from that, I wonder whether you can, tune that raw at different nodes or over time to achieve something better. Because here as far as I understood from the simulation, everything happens very regularly.
Right.
Time, right?
Right, so there are a couple of things there. So I mean, the way we frame this, rho isn't something you get to pick. Your rates are what they are. But right, maybe you say something like, I have a network with some sort of sum rate constraint, and then I want to say, well, where are the best places to put my rates such that things work better? Something like that. Otherwise, yeah, I don't think you I'm not sure we get permission to choose rho. Yeah.